So welcome to our first video with mathematical content in this course, Measure Theory for Probabilists. Today we are going to introduce set systems, and what I mean by a set system is just a set whose elements are sets. You might know this already from topology. There you have the set of open sets, but we will not have this, we will have other things. We will define so-called semirings, rings, and sigma algebras. In particular, sigma algebras will be very important for us, since measures, which we will define later, are defined on sigma algebras. So let's get started. With the measure theory for probabilists, today with the semirings, rings, and sigma fields. So set systems. That's the topic of today's video. So with 2 to the power of omega for some set omega, we are denoting the power set of omega, which is all subsets of omega. And we have here a set which is a subset of the power set. So C contains subsets of omega, but not necessarily all of them. Maybe, and we will also deal with this, you know about so-called topologies. Topologies are also set systems, but different ones. So we have semirings, we have rings, and we have sigma algebras, and sigma algebra and sigma field is just the same thing, and I will use them interchangeably. So semiring will be the most basic thing, and sigma field will be the thing that we are aiming at, because measures, which we are going to define, are usually defined on sigma fields. Let me start with an example, and then I come to the definition. So the basic example that we have is, well, we will also be dealing with this on one of our next slides. Let's say omega is are the real numbers, omega is R. And the set system C could be the following. Let's say semi-open intervals. A excluded, B included. A smaller or equal to B, and both in R. So this here is a set system because it contains of all intervals, and intervals are sets. So we will see that this C here is a semiring. It's not a ring, and it's not a sigma field. So what do we need to define this semiring? And as you see here, I can simply write this down, and I will not be able to simply write down a sigma field. So what do we have? We have here several notions that we need. We have intersection stable. A set system is intersection stable if A and B are in the set system, then the intersection is also in the set system. So when you have something like AB intersect with CD, when you think about this, that's also something of the same form. That's A maximum C until B minimum D. And that's an easy exercise. And this here is again of the same form, which means this here is also contained in C here. So this set system here is intersection stable. And what we will also need frequently, sigma intersection stable. And sigma always stands for, well, the same thing, but not just for 2, but for countably many. And I have a typo here. That's not I equals n to infinity, so I equals 0 to infinity. I have to write here, and the same here. Well, sorry for this. So that's sigma intersection stable. That's union stable. Okay, if A and B are in H, then the union is also in H. Let's have a quick look at here the intervals. These are not union stable. because, just drawing a short thing here, well, if I have AB here, if I have CD here, then of course the union, which is then this here, union with this here, that's not an interval, so the set of intervals is not union stable. Sigma union stable would be the same thing again, but for countably many such elements of H. Then complement stable. Well, that's what the word says. If A is in the set system, then the complement is also in the set system. Is that true for these intervals here? Well, probably not, because if you have here AB, the complement consists of this one infinite interval left of A and the interval right of B, and that's again not an interval, so the system here is not complement stable. And set difference stable, you have to be a bit careful. Well, set differences are, well, if you have A and B, you have B without A, so that's the set difference. And are the intervals here set difference stable? Well, at first you might be tempted to, it could be the case, A, B, and well, we could have C, C, D here. So what is then AB without CD? You have this here, that's an interval, right? So some set differences are again intervals, but not all of them. For example, if you have A, B, C, D, like this, then the set differences, so the set difference of the big interval from A to B minus C to D is a union of two intervals from A to C and from D to B. That's not an interval, so this set of intervals here is not a set difference stable. So these are the notions that we need. And now we can really define what a semi-ring, ring, sigma algebra, also known as sigma field, is. First of all, let me say we write this funny sign here, union with a plus inside, if A and B have no intersection. Then we write this here for A union B. So what is a semi-ring? And here we already need this notion here. A semi-ring is a set system which is intersection stable. And recall that we already saw that these intervals here, they are intersection stable. And that's another thing here. For all A and B in the set system, there are a finite number of elements in the set system, such that you can write B without A is this is called disjoint union of the CIs. Let's see here. We discussed set differences for the intervals AB minus CD, and you see, well, okay, that's okay, because that's the disjoint union of AC until DB. So this C here fulfills intersection stable and also the second property here. So we have that the set of intervals is a semi-ring. A ring, as a bit more elaborate, it also has to be union stable and set difference stable. And since the set of intervals is not union stable, as we saw, it's not a ring. A sigma field or sigma algebra has to have the property the whole set is in the sigma algebra. It's complement stable and sigma union stable. And the sigma is really important here. And if you have a sigma field here, then the pair set plus the set system is called a measurable space. So let's discuss this table here, which you also find in the manuscript. The full dots here denote the definition. So semi-ring has to be intersection stable and has to have this funny property. A ring needs to be union stable, set difference stable, and the empty circles here, these two here, they follow from these two. So for example, I claim that a ring is also intersection stable because it's set difference stable and union stable. So why is that? Let me just make a very quick proof of this here. I say A intersection with B is the same as, I have to be careful, A without B without A. Is that true? So let's draw a picture. A and B, A and B. So this here is the intersection. It was not true. Or was it true? Let's see. So I have everything which is in A, which is, well, B without A would be this here. So that was not correct what I wrote here. But what is correct? A without B. Everything in A, but not in A without B, which is this here. So the intersection just stays. So you can write the intersection as set differences. And since the ring is set difference stable, it's also intersection stable. And that's one thing. And, well, this circle here I also have to explain. Since the ring is set difference stable, I can even write B without A as a disjoint union of a single set here. So n can be 1 here. And that's the reason why this property also holds. Well, and finally, for the sigma field, but that's in fact simpler. So sigma field, what was this? The whole set has to be in this complement stable. And, complement stable, yes. Sigma union stable. And all other properties follow from this. So let's look at maybe one of them. Set difference stable. So let's look at this here. That's simple. So set difference would be A without B. And A without B is the same as A intersection with the complement of B. And since the sigma field is complement stable, I have that B complement is in the sigma field. It's also intersection stable, which I did not prove yet. So let me simply write here. A intersection with B is the same as A complement union B complement complement. I think you know this here. If not, then just draw a picture like this here and see that all the two sides are the same. So the sigma field is complement stable. So this here is in sigma field. This is also in the sigma field. The union is also in the sigma field. Because here, okay, it has to be sigma union stable, but then it's also union stable because you can just use the same set over and over again. So this here is in the sigma field, and then with a complement, because it's complement stable, that's also in the sigma field. So sigma fields are intersection stable. And for this reason, they are also set difference stable. Okay. And by this thing here, you see that every sigma field is a ring because it has the required properties, and every ring is a semi-ring because it has here the required properties. Okay, so let's come to some examples. First of all, our intervals, which we already had, and I made one restriction more than in the first slide. I have A and B have to be rational numbers. And I'm doing this because when I do this here, the rational numbers are countable, which means that this set system is a countable set system, which is nice, maybe. That's a semi-ring. We discussed this. Sigma algebras are not so simple, actually. There are trivial examples like, well, the set system consisting of empty set and the whole set. That's a trivial example of a sigma algebra. And the power set of omega, that's also a sigma algebra. That's also clear because, well, everything is contained in this. So it's also, in particular, complement stable, intersection stable, union stable, and so on. I want to make one more example here. Which is if you already have a sigma field on some set omega prime, and you have a map from omega to omega prime, then you can look at all pre-images of sets in the sigma algebra on omega prime. And I claim that this here, again, is a sigma field on omega. So why is that? And the reason are these two lines here, which we have to understand. So we need, for example, to understand that this set system here is complement stable. Which means if this set here is in the sigma algebra, then its complement is also in the sigma algebra. And the reason is this equality here, which I explain to you in a second. So the complement of the set here is the same as the pre-image of the complement. And since the complement is in the sigma algebra here, because f prime is a sigma algebra, this object here is here complement stable. And a similar argument holds for countable unions, because the union of pre-images is the same as the pre-image of the union. So let me draw one picture maybe for the complement, or maybe you know this, but then let's record it. Let me take a simple example. So omega is here, omega prime is here, and let's use a map or a graph like this here, well, like this, and I have, let's say, set A here. So on the one hand, I have the complement of the pre-image of A prime, that's A prime. So what's here? Well, I have to draw it like this. So down here, down here, down here, down here. So the set consisting of the union of these two here, that's f to the minus 1 of A prime. And the complement is then, of course, all here, all in the middle, and all to the right. That's the complement of the pre-image. And then the pre-image of the complement, well, I would have to take these two here and take the pre-image. And again, have exactly this set here, union with this set here, union with this set here. So these two are the same. And that's the reason here for complement stability of this set system. And similarly, you can draw a similar picture for unions and also for countable unions. And that's the reason why this here is then again a sigma field. Well, that's enough for today. And in the next video, we will continue, and you can already look at the manuscript, what we will do then. See you then.